Okay, now in previous years, in this module, when we came to this part where we started talking about the digital control systems, my audience, my class usually haven't had any exposure to that before. Today it may be different because some of you would have done the MBB 410 module last year. And for the last 2 years, I have actually discussed digital control systems. Let me perhaps rephrase what I was going to say. In previous years, we limited the discussion of digital control systems in the final year MBB 410 module just to a very brief introduction, just explaining basically what digital control is, but stopping short of even defining the Z transform. But for the last 2 years, I've included that in the MBB 410 module, even though the additional part was not examinable. It wasn't it wasn't defined in the course definition in the yearbook. So, but I did actually spend quite a bit of time on that, even though it was kind of optional. So there's a possibility today that some of you may have actually studied this already. So I've decided also then to remove it formally from this module. In other words, what I'm talking about now is classical control treated with the digital control. But what I have, if you're in a situation that you also haven't had any exposure to digital control systems or even digital systems before, I have actually last year, for the MBB 410 or for the undergraduate module, I've made an extensive array of recordings of this, and I've now made this available to you on ClickUP in the MBB 780 module. So if you feel that you're lacking there, or if you've never heard of it before, you're most welcome to view those recordings. And even if you have done this before, but you would like to polish up, you can then also use it for that. So I'm not going to spend too much time on that. I'm very briefly going to talk about it. Now that set of recordings, now by the way, let me just be very clear, but I've also tried to indicate that in ClickUP. The part that I now consider not formally part of this module is classical control when it comes to digital control systems, quite in the same way that the classical control for analog systems were also not part of this module earlier. But unfortunately, some of those things that are covered, you really need to have a little bit of understanding of that, even to apply digital control systems to the state space methods. And of course, applying digital control systems to the state space methods, there's no recording for that yet. I'm now making the recording for that, but it will be on ClickUP a little bit later. And that certainly is part of the module. And then if we deal in the digital control, state space control with issues that is really covered in the classical control, then of course you need to try to understand that. So even though I will not specifically examine you on that, you may not be able to progress with the state space digital control systems if you don't cover that yourself. So I'm most welcome to assist you also with questions, if you have questions on the classical control as applied to digital systems. Now that whole set of recordings starts off with a recording where I actually derive what is on this slide, the time delay. And this is actually it forms the basis of much what we do in digital control, but it's actually wider than that, because it's also used when you have a classical, a control system where there is a transport delay. The very good mechanical example of that would be like something like a steel mill where you've got this red hot plate of steel that goes through a roller set, and the distance between the rollers needs to be controlled to get the thickness correct. But the thickness, especially in the olden days before they had these fancy optical ways of measuring displacements and distances and thicknesses and stuff, they had to wait for this steel to move a little bit downstream so that it can cool off so that its thickness could be measured. So the measurement is made quite a while later, after the steel has gone through the rollers. And the fact that you have that delay in time, that is called a transport delay. And so it introduces this e to the minus st, where t is the delay time. It introduces that. So in other words, what this time delay slide just tells us is that the Laplace transform of a time function, just the small f is just a time function, but the time function is delayed by capital T. So the Laplace transform of a time function that's delayed by a capital T is simply the Laplace transform of the undelayed time function, which we can indicate as f of s, as seen right at the top here. This is the Laplace transform definition. So the Laplace transform of the undelayed time function f is capital F of s. And so what we've proven with this little recording, and you can, if you don't, you're not comfortable with this, please read, please go through that. But what we've proven is that the Laplace transform of a time function that's delayed by a period capital T is simply the Laplace transform of the undelayed function multiplied by e to the minus s times the delay. And this function is then also, it appears quite a bit in digital control. So I'm not going to spend further time on this. I'd like to then next move on to, it's actually in the same slide set. After having gone through that recording, then the next recording introduces digital control from very basics. So you could just go through that. The important thing here is that we work with these sampled signals, and this is true then also in state space control, that instead of having a continuous signal, you have a sampled signals which can be represented by these series of impulses, which really means that as they are represented here, they are of limited length, limited height, because it's the signal are at the sampling instances, but the way that it's mathematically presented is actually with this equation 13.2, and the star indicator here indicates that it's actually a series of real impulses which are infinitely high, because it's actually the values indicated in this graph, each of them multiplied by an impulse. So this actually makes these, the magnitude of this signal is actually infinite at the sample instances. But it's a scaled infinite, so some infinites are larger than others, if you wish. And in between they are actually zero. And so you need to wrap your head around that also, because the properties of impulses are actually used in doing the mathematics. But so take note of that, and then you can go through the rest. This is just representations of the sampled systems, and then this recording then ends up by showing what is the Laplace transform of a zero order hold, which is used to convert your digitized signal back to an analog signal. And exactly here, the time delay function is used to actually prove that the transfer function of a zero order hold function is of this nature. So that is the second recording. Then the third recording then introduces the Z transform. Now, if you use you will see this a little bit later this morning when we use state space methods for digital control. It's still in the time domain. So in just dealing with state space, you don't really need to work with a Z transform. But when it comes to actually implementing that controller, you need to transform your system to the digital domain, and for that it's important that you understand the Z transform. So you can work through the Z transform, and then after introducing the Z transform, this set of slides and the corresponding recording then introduces the pulse transfer function, which is really the equivalent of the S domain transfer function for continuous systems in the Z domain for discrete systems. By the way, I've now not mentioned it, but it boils down to this, that if we have a continuous system in classical control theory, you deal with it in terms of transfer functions in the Laplace domain. This you all know by now. But if we have a digital system, instead of using the Laplace domain, we use the Z domain, And the Z transform is used to then either transform the time domain system to the Z domain, or the Laplace domain information to the Z domain. Okay, so this is then the pulse transfer function is then introduced, and various properties of that is then also discussed there. So that is the what is this now? The third recording set. Then the fourth one is perhaps a little bit less important in the context of what we're going to do. It just shows how it starts off by showing how one can do the inverse Z transform through long division, but then towards the end it also discusses further properties of the Z transform. And then lastly, the last recording in that set deals with the implementation of a controller of which the Z transfer function, in other words the pulse transfer function, is known. Sorry, this is not what I should show you. It's let me just go back in the slide set. So for instance here in this, you can think of this as simply just a transfer function of an output with respect to output Y with respect to input R, but in the Z domain. So you've got the Z domain transfer function in terms of the Z domain variable Z. And this recording then shows how you can rewrite this transfer function as a temporal recursive algorithm. And that is one way of actually coding it in a computer. So for instance, you could have designed a, let's say a PID controller or a lead controller or a lag controller, ending up with some other transfer function, like similar to what we have here. And using this theory, you can then convert that transfer function into a recursive algorithm in the time domain that you can very easily code into a computer. And so that will then create your controller on the computer for you. So it's a very practical, even though it may seem very abstract and very theoretical, it's actually a very practical issue. And so this controller is also called an infinite impulse response filter, because a controller is always a filter. In fact, you can think of any dynamic system as a filter of some sort. So the controller, going this route, we really cast our controller into an infinite impulse response filter, and that is very easily coded with this recursive algorithm. So you can look at that also, but this is not it's almost also background information, because in this module we're going to do this in a we're also going to use a kind of recursive algorithm, but not this one. So this is like a parallel route to getting to the same destination from the one that we're going to discuss next in the context of state space. And by the way, the two routes actually give identically the same results for the same system. Okay, so I think this is then enough said of all these background things. Perhaps I should invite you, are there any questions at this time? Everybody happy still? Okay, then I'd like to now start with state space modeling of digital systems. So maybe I should just stop the recording and restart it in order to have the recording not too long. So just bear with me for that for a moment, please.